I haven't announced any of our seminar talks this semester. And in fact, I didn't even announce this to the other section. In fact, I haven't even told you guys about the PCHEM talks we had this semester, though most of you, I think, are in, a good chunk of you are in seminar. If you want to come to a chemistry seminar, this would be a good day to come at 2 o'clock on Friday in the seminar room up on the third floor of the college. We're having Alicia Wagner. She is one of Dr. Trilla's old students from about 5 years ago. She just graduated. Well, she hasn't even graduated yet. She just defended her PhD at Northeastern in organic chemistry, and Dr. Trillo invited her to come give a talk about her PhD research. Alicia's a really, really good organic chemist and young. So I'm really excited to have her. I usually like to invite young chemists because typically the seminar programs invite older chemists, prominent chemists, and I think we should give opportunities to younger people. This is in some sense the youngest professional we've ever had. And so I'm really excited to have Alicia. She's really cool. So if you're free Friday afternoon, come see her talk. Okay. Other than that, we should tackle today. We are in position finally to tackle the radial part of the hydrogen. We've spent a week on angular momentum and spin. We've done enough on those two topics now to get a kind of qualitative or even a quantitative understanding of what the angular momentum structure of hydrogen looks like. We have to finish the radial problem, the part with the electrostatic interaction, right? That's our final step in hydrogen. And by then we'll be able to account for all of the forces that the electron feels in hydrogen. We'll be able to write down a Hamiltonian, right, an energy operator, and then we'll be able to solve for our wave functions, right? We're not going to do the mathematical solution to this problem in the sense that I'm not going to solve it and like from first principles, right? What we're going to do is I'm going to set the problem up. We're going to talk about the hydrogen problem qualitatively, right? We'll look at some math, see at how we think the wave function will behave at certain limits, get a sense of what the solution looks like, and then what we'll do is we'll skip some math, right, which is not important to get the final answer. And so we'll at least have some qualitative and some conceptual understanding of what the electron is doing in the hydrogen atom, and then we'll get to the final solution of it. And it will help us contextualize the fairly complicated mathematical structure of the hydrogen atom in the sense that we'll be able to break it into small parts, right? There are certain behaviors that the electron does at certain distances from the proton. We'll talk about when it's really, really close to the proton. We'll talk about when it's really, really far from the proton. And we'll find that there's a way to kind of connect those two behaviors together in the intermediate region for the wave function. And we'll have a complete picture of the hydrogen's behavior this way, right? So we're going to kind of just put everything together into small parts and build it up into a greater whole. We've got a little bit of work to do before we get there. What we'll have at the end of this class are wave functions. We'll be able to say, hey, this electron is in a certain state, 1s, 2s, 2p, 3s, whatever you want. We'll understand what those s's and those 3's mean as numbers. And then what we'll do next week is think about properties of hydrogen. Once we have the wave functions, we can calculate anything we want about hydrogen. Anything. We know everything about hydrogen at that point. So we'll start exploring hydrogen in more detail next week, which will lead us into helium and other atoms too. All right, so we've got maybe a week of atoms, maybe 3 lectures left of atoms, and we're going to just finish up with molecules for the rest of the semester. Put atoms together. Okay, so let's think about where we were. We're look at the radial problem. Hydrogen. And I always like to start with an axis system. Let's just remind ourselves what this problem looks like. At this point, it's probably burned into your eye sockets, your eyeballs. We have a proton in the center of our coordinate system. And there's a vector, and our displacement vector, which we call R, pointing to our electron, right, which has some position in space. Right, there are 2 forces that we have to consider in this problem. right? The one that we're going to work on today is the electrostatic problem, the electrostatic potential. Right? I'm relating force and energy together. By saying potential, I mean the energy. There's energy of the electrostatic force. Okay, we're always dealing with energies, not forces here. Right? But when you think force, again, think of a corresponding potential energy associated with that force. And that potential, the function of just r, the distance, and it's minus e squared, which is the charge, the fundamental charge of the electron, divided by this 4 pi epsilon naught constant times the distance r. Right? This is a negative potential. Right? This is attractive at all positions because it's negative. V is always less than 0 or equal to 0 at infinity. Right? The only place where there is no electrostatic attraction is where the proton and the electron are infinitely far apart. Okay. Right? So this is a vacuum effect, right? This is a sucking effect. There's always this force from the proton pulling, or the nucleus in general, pulling the electron towards it. Right? It acts as a vacuum for the negative charge. This has to be compensated by another force to get a stable orbit, right? Which is the force due to angular momentum, right? Which is the centrifugal potential, right? Which pulls the system out. Right? And that potential we'll call V centrifugal, which is a function of r as well, but it's equal to L squared over 2 times the moment of inertia, which we evaluated already for this problem. It's h bar squared L plus 1 over 2, and then times the moment of inertia, which is the mass of the electron times its distance. Okay, so in terms of, so what we're doing is we're saying, hey, we've got the electron at some position r, right? It feels an electrostatic force pulling it in, but that electron has some fixed angular momentum, right? We're not thinking about theta and phi here. We're assuming that the system is moving in a theta and phi space at some angular momentum, and that angular momentum is indexed by the quantum number L, right? These are just integers here, right? And this is a positive potential force, right? It's a positive number. Everything here is positive, right? This is a force that pushes the electron away, right? So this is a repulsive force. And V is always greater than or equal to 0. The only place where this is 0, of course, is where the electron is at infinite distance, right? Where r is infinity and V centrifugal is 0. Okay, so we have we have 2 limits that we have to think about in this problem. If we're going to do some limiting kind of law, think about what this looks like at the limits. We have the 2 obvious limits are r equals 0, right? As the electron gets closer and closer to the proton. And then there's also a limit at r infinity where all the potentials turn off. Okay, so there's going to be kind of an uninteracting region at long distance and then a highly interacting region at short distance. So we're going to have to consider the limits of both of those, right? The physics near the proton are very different than the physics on the outside. But we know because of quantum mechanics that the wave function that defines this behavior is smooth and continuous. So there has to be some smooth function that connects this high energy, fast motion close to the proton to the slow motion, very little energetics, very little potential energy at long distance, right? There's going to be some smooth function that connects these 2 limits. We're guaranteed that by quantum mechanics. So we're going to have to figure out how that function smoothly moves between these 2 limits, where the potential energy is large at close distance and the potential energy goes to 0 at long distance. Okay. So again, what we've done here is we fixed the system to some fixed angular momentum, right? So unlike the other problem, when we were looking at angular momentum, right, this means we have some L here is equal to L h bar. Right? The angular momentum is equal to LH bar, just some fixed amount, right? This is the opposite assumption we made about the angular momentum problem, where we fixed R and varied theta and phi, which of course changes your angular momentum at constant radius. And here we have the opposite case. We're looking at the system at varying radius, but constant angular momentum, constant theta phi behavior. And so we're fixing. And that's, we can do that because again, angular momentum is only dependent on theta and phi. This is dependent on just R. They interact independently of each other. These two forces act independently because they're functions of different variables. Okay. So what we have to do now is take these, right? We have all of the energies that are, all of the potentials that are acting on this electron. We can put them all together into one big operator that is the total energy operator, the Hamiltonian. All right, so we're going to start constructing this Hamiltonian for the radial problem. All right, what we're going to do is first define a total energy operator. And it's going to be a sum of the radial part of the energy plus an angular part, theta phi. All right, we can separate the two, right? Because the functions that depend on the potential energies are separable as well. Right? The potential, because of angular momentum, is only a function of theta and phi, not R. So we can separate the energy into two parts. We've already done the theta and phi part. We've talked about that. So we're going to focus on HR here, right, the radial part. And what we're going to do is say, if these are two separable, what we can do is we can write a total wave function of the electron, or of the hydrogen atom, if you will, as a product of the spherical harmonic, the angular momentum wave function, times the radial one. So it's going to be two functions. One is going to be YLM theta phi, that's our angular part. And we're going to multiply it by some function we haven't determined yet, which we'll call R, big R, that has some dependence on L, some other quantum numbers maybe that have some indices. We don't know them yet. And that's a function of R. Okay, so we have a product wave function of two different parts, and we have a summed energy. So when we have an energy of two different sums that are separable, the wave function is going to be a product. The total wave function will be a product of these two energies. All right. So what I can say very quickly, when I put these two together, when I apply the total energy to my wave function, this is going to end up being the Hamiltonian for the radial part operating on the radial part of the wave function, plus the angular part of the energy operating on the spherical harmonic. Okay. So we can just separate everything into two parts and deal with them separately. That's what we've been doing this entire time, saying everything separates nicely. The energies just sum together. And we already know the answer to this question, to the angular part. But when you evaluate this, you get h bar squared L plus 1 over 2 me r squared. Okay, so that's the total energy of angular momentum. And this is equal to the L operator squared divided by 2I. Right? So this is the total angular energy due to angular momentum. Bless you. Right, so we already know that part, right? So we've already solved half this problem, like I promised, right? We put in 2, we've solved the angular momentum part. We just have to finish the radial part. Right, but notice notice that when we evaluate this, we get an R squared out here, right? So we have some energy, right? The angular momentum energy, the centrifugal force, is dependent on the distance between the proton and the electron. And so this total energy, in some sense, is a function of R. And so HR is going to depend on it as well. And so we have this additional term we're going to have to bring in over here. So let's go ahead and put everything together into one nice big package. So HR, the radial Hamiltonian. Well, first it's going to be, we'll write it in three different parts. It's going to be the kinetic energy of the electron. Along the radial direction, plus the centrifugal potential, plus the electrostatic potential. All right, we have three forces or three energies that need to be tracked, right? The kinetic energy along R. We've already done the kinetic energy along theta and phi. That's the angular momentum part. So we only have the kinetic energy along R left. The centrifugal potential, the R 1 over R squared, and the electrostatic potential, which is minus 1 over R. Okay, so once I put all of this together, so we put all of this together, we have something that looks kind of nasty. Okay, so this first term, I'll write in gold, is minus h bar squared over 2 times the mass of the electron. And then we have this strange second derivative term with respect to R, which is 1 over R squared times the derivative with respect to R times R of R squared times the derivative. I'll kind of just put it like this instead. Right, this is that second derivative term, right? Remember, the kinetic energy always dependent on the second derivative of a coordinate. But when we convert to spherical coordinates from x, y, z into r, theta, and phi, we get this kind of funky looking thing. But again, it kind of looks like the second derivative with respect to r. It's the derivative of a derivative. And there's some additional r squared terms that arise due to the coordinate change between x, y, and z in spherical coordinates. So that's our kinetic energy. And the other terms we can just write down from before. We have minus h bar squared L plus 1 over 2 me r squared. And then the electrostatic potential, which is negative. I'll do it in a different color. Minus e squared over 4 pi epsilon naught r. Right? And this whole thing multiplied, evaluated by the radial functions, which are wave functions or radial wave functions, put a question mark there, R, is going to give us some energy out, radial energy times R. Right, so this is just a Schrodinger equation. It says the total radial energy, when we evaluate it for the radial wave function, we get the energy back times the radial wave function, right? This is just h psi is equal to e psi, right? This is just the Schrodinger equation. But just with a bunch of extra terms. So we have this Hamiltonian, that's the total energy. We know that the proper wave functions will give us a number back times the wave function, right? That's the Schrodinger equation. Right, so how do we even start thinking about this problem? Right? This is not one of those things when we did the particle in the box. Remember when we did the particle in the box, we said the wave functions satisfy this behavior. That says when you take 2 derivatives of the wave function, you get it back times a number. And we got these sines and cosines. Well, what this is saying is you take a second derivative, you also get some r squared and 1 over r and 1 over r squared terms that come out of the second derivative. It's pretty messy, right? It's a much more complicated relationship. Right? When you take a second derivative of the function, you get a 1 over r squared and a 1 over r out. It's a little funky. Right? So it's not really obvious what these equations look, the solutions to this equation look like. Right? So if your eyes glaze over, that's okay. They should. Right? It's not that easy. It's one thing to write things down, it's another thing to solve it all together. All right, so what I want to do is give you some insight how we solve this problem. How can we simplify this to get a better picture of what's going on? What do the radial functions look like? Well, I'm going to make a substitution. So let's do a little bit of algebra. I'm going to make a substitution. I'm going to create a new function, define a new function u, which is just r times my big R function. Right, so I'm just going to replace my radial wave functions with the radial wave function times the coordinate. All right, and then what I'm going to do is I'm going to plug this into this equation and do the chain rule on it to get a differential equation, some calculus with respect to u instead of with respect to r. Okay, when I do that, what I end up getting is an equation that looks like this. It says that the second derivative of u with respect to r is equal to minus 2m e over h bar squared times the energy, radial energy, plus e squared over 4 pi epsilon naught r minus h bar squared, L plus 1 over 2 me r squared, u is equal to 0. Okay, so the advantage of by solving for a function u, which is r times little r, what I've done is I've simplified out all of this junk here with the minus 1 over r squared and the r squared. Right, I just get a second derivative of u with respect to r. Okay, so I go back to kind of a Cartesian looking derivative, right? It just looks like a wave function's derivative, second derivative. Okay? So I've just manipulated the function a little bit to simplify things. And this doesn't equal to 0. I apologize. It's not equal to 0. Some of these are equal to 0. So what it's saying is that when I take the second derivative of this u function, I get u back times some number, right? Something that looks like a number plus 1 over r minus 1 over r squared. Right, so I can kind of say, I'm just going to kind of like assume all of these numbers are equal to 1. Right, so I just make it unitless. This looks like minus 1 plus 1 over r minus 1 over r squared u. Okay, so it says when I take the second derivative of whatever this function is, I get the function back times this like inverse polynomial, right? It's going down instead. You get, every time you take a derivative of u, you get a factor of 1 over r, right? And then you get a factor of 1 over r squared, right? So that's the opposite of the harmonic oscillator. In the harmonic oscillator, the functions that satisfy the harmonic oscillator Hamiltonian, when you take the second derivative of them, you get the function back times a polynomial. So r plus r squared. Right? So this is a function that goes 1 over r minus 1 over r squared. So that in some sense the polynomial that comes out of the derivative is going in the opposite direction in powers than it is in the harmonic oscillator. And again, the reason why that is because our potential now is proportional to 1 over r, or 1 over r squared, whereas in a harmonic oscillator, it was proportional to distance squared, right? It's a positive polynomial, it's x squared. And here the potential is x to the minus 1 minus x to the minus 2. So we get this addition. So our functions now have to give us back inverse polynomials, inverse functions of r, instead of positive functions of r, positive polynomials of r, because again, the potential is inverse. not proportional to the distance. It's proportional to the inverse of the distance. So we've got these functions that look, we don't know what they look like. All right, it's not really obvious when we think about it what kind of function, when we take two derivatives of it, we get something that looks like this times the original function. Okay, that's not that easy to think about. Okay, but there is a solution to this problem. Right, there is a u I can write down, a radial wave function I can write down that satisfies this behavior. Right? I want to get a picture of what it looks like. Right, so we can't immediately solve this times this. If you've taken differential equations, which I doubt anyone here has, be one person, you might be able to solve this problem. I find it to be somewhat tedious, but I think it's better to look at it from a qualitative point of view. All right, so let me go ahead and copy this equation over. And what I want to look at are the limiting cases of this equation. So I want to take two limiting cases. We have identified those two limiting cases. They're when R goes to 0, where the electron is really, really close to the proton, what happens to U? And then when the electron is really far away, what happens to U? What do the functions look like at their limits? Okay, so first we'll look at two limiting cases. So first we'll look at R goes to 0. Okay, so what happens to the potential energy as R goes to 0? Well, these two terms get big, right? They get quite large, right? Because they're 1 over R, they get exponential. They don't get exponentially large, they get polynomial large, inverse large. Right, but which one grows, which one becomes more positive more quickly? Well, 1 over R extends as 1 over R. Obviously, 1 over R squared is much larger at small r, right? Because it's R squared. So what we can say is that 1 over R squared is much larger than 1 over R. And so what we can do then is neglect the 1 over R term. Right, in this system, the system is defined, the energy is mostly defined by the centrifugal force. Right, so the centrifugal potential dominates. And so our function simplifies, our equation simplifies to the second derivative of U with respect to R squared is equal to 2me over h bar squared times minus h bar squared L plus 1 over 2me R squared. Times U. Right? And that's equal to, well, we'll just do some math, right? We can cancel some things out, right? It just is proportional to L plus 1 over R squared U. And it's positive. Right? Of course, it's positive because it's a centrifugal force is a positive energy. Positive potential pushes the electron away. It's positive. Right, so now we have a much simpler equation to deal with. What we're saying is that whatever this U is, the second derivative of it gives me back a factor of 1 over R squared. Okay? Right, so that's a much easier thing to solve. And what you find is that U, there's two possible solutions to U for this equation. And I'm not going to solve for any of the constants or anything like that. We're just going to look at it roughly. You get a number A times E. All right, I'm going to write it EXP times something, just to simplify it. Just remember, I'm going to put it over here, that EXP of X is E to the X. If you've never seen that notation, that's what that means. All right, so whenever you see EXP, just think E. It's the square root, so it's 1 over h bar square root of 2 ME times the total energy of the system times R plus B exponential of the negative version of this. Right, so the function looks like e to the R plus e to the minus R. Okay, so I'll just write that here, right? It kind of looks like a e to the KR plus b e to the minus KR. Okay, where k is just some number. Okay, we don't have to worry about the values here. This is just a kind of an approximation, right? We're just looking at the behavior. All right, so it's not clear, right, what this should be. But remember, it's a wave function, right? What do wave functions have to satisfy? Well, their integral over all space has to give you a value. They can't diverge. So we have to have a wave function that when you take an integral from r equals 0 to infinity, that you get a value. It doesn't go to infinity, all right? Well, the integral of e to the kr is divergent, right? So it can't be e to the kr, right? Just by the nature, right? This is not physical because it diverges. Right, so that means that there's only one possible functional form for the wave function near the center of the atom. Right, it says that U is equal to B to the E minus KR, which means that R in this area looks like 1 over R e to the minus KR. Because U is RR. U over little r is R. Big R. Right, so it's an exponentially decreasing function. It looks like an exponentially decreasing function near R equals 0. So if I were to draw a wave function as a function of R, right, we don't know exactly what it looks like at long distance, but it looks something like this. Right, it decreases exponentially. That's at near R equals 0. What about R infinity? Oh, sorry. What did I screw up here? I messed something up here, guys. No, that's right. That's right. That's right. No, sorry, this is the wrong solution. Hold on to that for just a second. I apologize. I apologize. I missed my answers. Okay. So forgive me. I'm going to go ahead and put this on the next page because this will be our next limiting case. All right. I know this is going to fuck your notes. I apologize. All right. So the solution to this instead, I know something seemed wrong when I was doing that because the equation didn't work out. All right. So the solutions to this, I apologize. What we see is that there's only one solution for this. It's that U is proportional to R L plus 1. Okay, there we go. That's a little better. All right, so it looks like a polynomial. All right, so nearby R equals 0. And so that means that R, the big R, looks like R to the L. Okay, there we go. So near R equals 0, it kind of looks like a polynomial. Okay, it looks like R to the L. Okay, sorry about that. All right, super easy solution. Let's go back to this one. This is the solution at R infinity. Okay, this is where 1 over R is approximately equal to 1 over r squared, which is equal to 0. Okay, that's better. And so that means that the solution, the equation that we have is the second derivative of u with respect to r is equal to minus 2m h bar squared times the energy times u. Okay, so this is much easier, right? It says that the function u looks like at long distance, a function that when you take two derivatives of it, you get u back. That's an exponential function. Okay, so at long distance, let me fix my plot here. Right, so at short distance, right, a short distance, it looks something like this. And then at long distance, it looks something like this, e to the minus kr. Okay, I don't know what it looks like in between, right? But in some sense, it's going to be increasing. It's 0 at r equals 0. It increases to some value, and then eventually decreases to 0 at the limit. Right? I don't know what it looks like elsewhere. Just kind of mark it for the question. Okay. All right. Sorry about that. Got it perfect last time, and then I got it flipped in my head today. Okay. So we have a function that increases like a polynomial at short distance and then decreases like an exponential at long distance. Okay. That's nice. So that should tell us something about the solution of this problem, right? That the functional form, when we take limits as r goes to 0, it simplifies to a polynomial, and at r at long distance, it simplifies to an exponential. So whenever we take the two limits, those are the results we're going to get. So that's helpful, right? That tells us a little bit about what's going on. We just have to get clever about the connective tissue in the middle, right? What does the function look like in the middle? Right, that's a trickier answer. Right? It's not really clear, but I've provided, in some sense, I've provided a framework for us to know how to solve this. Right, the potential, the wave function at long distance has some numbers b and a that I could fit. Right, I could figure out what those numbers are. And then in my polynomial part at early distance, I can do some calculations with my differential equation, my Hamiltonian, to figure out what the coefficients of the polynomial are. Right, so that'll give me a quantitative answer for the long distance and the middle distance. And then what I need to do is find a function to multiply in the middle that connects these two parts together. Right, remember that the total function needs to be continuous and smooth, meaning that the derivative doesn't have any cusps in it. There's no really weird discontinuities. Nothing weird is happening in the wave function. It needs to be a smooth, basic function, analytical, as we call it, right? Which means it has an analytic derivative that exists everywhere. It has an integral that's finite, and it's also orthogonal. Right? And so we have to come up with that connective tissue that provides all of those properties. And connects two limits together. This connective part. All right, that's the hard part of this problem, is figuring out what that connective tissue looks like. So we need to smoothly connect the two limits together. Right, and that's the part I'm going to skip. Right, I'm going to give you the solution now to the final wave function. Right, and we'll look at examples and plot them. Look at what they look like today. All right, and I'll talk a little bit about this connective piece. This part that we don't know about. Okay, so we put this all together. So I'll go ahead and copy that picture over. I think it's a nice picture. And we'll use that color scheme for my labeling. Great, so we've got the final solution, the full solution for R. Great. There's some quantum numbers associated with indices. I'll write them down in just a second. There's two of them. There's n and then our number L. And of course, the radial function depends on the angular momentum number, L, because it's in the potential, right? You got to specify L for the system. That defines the centrifugal force. So R is a function of this L number. And there's this new number N, right? This new number we haven't seen yet, N, which is a new quantum number for the system. And it's what's called the radial quantum number, right? That's an old term for it, but N is the quantum number associated with different orbits of different radii. I'll go ahead and write that down in a second. So let me go ahead and write the whole equation down for you, completely generic. First, we have a normalization constant. This ensures that the square of the wave function is 1. N minus L minus 1 factorial over 2 times N times the factorial N plus 1 cubed. And this is all square rooted, right? So this is our normalization constant, a part of it. There's one more term that we have to add. Right? And it's multiplied by this spatial term, 2 over N times this new number, which I have not defined yet, but I will, called A naught. This is a new constant. And this is to the 3/2 power. Right? You get one factor, you get a factor of square root for each degree of freedom, X, Y, and Z. So you get 3/2 here because there's 3 dimensions, spatial dimension. Right? And then we have the short distance range function, R to the L. And then we have the long distance behavior. So E to the, bless you, E to the minus R over N A naught. All right, I'll define A naught in a second. Let me go ahead and give it the right color just to keep it consistent. So this is our long distance, right? This is R, so it's our short distance, R goes to 0. And this is our long distance behavior, so R goes to infinity. And then we have the connective tissue in the middle. And that's a new special function, which I give the label L. And it takes in 2 numbers, N plus 1 and 2L plus 1. And it's a function of the quantity 2R over N A naught. It's a function, it's like f of x. This is our connective tissue. Right, the special L function. Remember, we had these special polynomials in the harmonic oscillator that I give a label to. Right, these special ones that provide the orthogonality to the wave functions of the harmonic oscillator. Right, there's these polynomials that give the wave functions for the harmonic oscillator their oscillating behavior inside the potential. Like gives that wave behavior. This is exactly the same idea. Right? You have this special polynomial that provides orthogonalization. So L N plus 1 to L plus 1 is called a Laguerre polynomial named after its inventor. Right? And it's just a polynomial. It's a function of R. Right? So it kind of looks like R to the 0 plus AR1 plus BR squared plus dot, 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 dot. Right? It's just a polynomial. It's a special kind, all right, that are calculated, and they're fully tabulated. In fact, I provide them a list on Canvas, though I don't know if you'll ever actually need them in the class. Right? They're fairly common. You can find them on Wikipedia. They're really well-known solutions. Really well. This is a well-known differential equation problem, this central potential problem of something rotating around a spherically symmetric potential that's attractive. These are very generic solutions, and so they're well tabulated. Okay, well, I'll give you some examples today as well. They're just polynomials. All right, and so we have a couple of new numbers in here that we should specify. Right, so we have 2 quantum numbers now. this new quantum number n. We have two names for this. First, sometimes I call it the radial quantum number. But more traditionally, by chemists, it's called the principal quantum number. And n can be any number but 1 or greater. Okay. And you know what L is. L is the total angular momentum, the orbital angular momentum. And it has a new constraint. Now, L can only be between 0 and n minus 1. Okay. So L is limited by the value of n. All right, remember that I said before, we said, hey, there's L equals 0, there's 1 orbital, L equals 2, there's 3 orbitals, L equals 3, there's 5. This enforces that structure, right? Let's just double check that. If n is equal to 1, that's the ground state. There's only 1 orbital and n equals 1, that's the 1s orbital. And L can only be between 0 and n minus 1. N is 1, so this is 0. So L can only be 0. Right? So there's a 1s orbital and only a 1s orbital. And then in n equals 2, L can be either 0 or 1, 2 minus 1. So that means L can be 0, which is the 2s. L can be 1, that's the 2p. And there are 3 of those, because when L is 1, m can be minus 1, 0, and plus 1. That's your x, y, and z p orbitals. Right, so this is the same structure for electron configurations that you've known and either loved or hated your entire career here. Right, now you can see them actually borne out. They are enforced by this structure of the Hamiltonian and the wave function. Right, that the only valid orbits are these quantized ones, 1, 2, 3. Right, these are our Bohr-like orbits in the Bohr atom, the Bohr hydrogen atom. These little concentric orbits around the proton. These correspond to each of these orbits, but L could take a number of different values for each one. Right? This is in some sense where Bohr got it wrong. Bohr said that n equals 1 has to have angular momentum. It doesn't. Angular momentum, the total angular momentum of n equals 1 is 0. Right? So Bohr was kind of wrong and also kind of right at the same time. Okay, so let's look at some functions. All right, let's just write a few and then plot them. Okay. I don't really emphasize too heavily these functions. We can do very useful calculations with them, but in some sense, you understand what these look like. You've been looking at 1s orbitals and 2s orbitals and p orbitals and orbitals your entire career. Those pictures have not changed, but we'll gain a little bit of insight about what they look like today. All right, so let's do some examples. I'm going to make a little table here. All right, and now we have quantum numbers n, l, and m. All right, we have 3 quantum numbers for the hydrogen atom now, right, at this very moment. All right, I'm going to write down the wave function, which are going to be theoretically products of r, theta, and phi. And I'm going to multiply together the r part in L and the spherical harmonic. Okay. And then we'll give it a label. We'll give it a name. Okay, so let's start with the basic one, 1, 0, 0. Right, we call this the 1s orbital. And the total wave function for this problem is 1 over the square root of pi. Let me make actually two things. How do I want to do this? Yeah. All right, so define 2 things. Let Z be the nuclear charge of the atom. Right, this is the same basically the same as the periodic number. Right. So for hydrogen, it's 1. Okay. And then I'm going to create a reduced radial variable called rho, which is ZR over A naught. Oh, I haven't told you what A naught is. Okay, I'll do that in a second. It's just a number, and we'll interpret it in just a second. I'm sorry that I haven't done that yet. All right, so this is just a unitless distance. Okay, with that now, I can write the functions. It's Z over A naught to the 3/2 e to the minus rho. Okay, so this is the 1s orbital. Notice it has no theta or phi dependence, as it should not have any, because it's a sphere, right? Remember that the s orbital, the sphere, is the spherical harmonic for the s, the L equals 0, is a sphere. It has a constant value at every angle. So there is no angular dependence on it. So there's no theta or phi in here. And what it says is that the wave function just decays away from the center of the atom as e to the minus r, or e to the minus rho. Rho is just think rho is a distance, a unitless distance. All right, so this just looks like a sphere, but it's not really a sphere, right? So in terms of angular distribution, when you fix r, you put your electron at a fixed radius. The value of the wave function is same everywhere, but the wave function decays as e to the r. So there's a region, kind of intermediate region in the wave function, where the electron is going to be prefer to be, right? But in some sense, it can be anywhere in terms of distance, right? The only time this is 0 is that when rho is infinite, right? So theoretically, when you draw that 1s orbital picture that you see, that's only giving you in some sense the shape of the angular distribution of the system. In reality, that in terms of distance away from the center, the wave function is infinitely extended. So if you go look at a hydrogen in the 1s orbital, yeah, on average, it's going to be near the proton, some distance. But in general, you might have a probability to find it on Mars, right? Or in Gary or something. Right? There's always a probability that the electron is somewhere else. So having these pictures of like fixed spheres, like the spherical shell that we call the 1s orbital, is somewhat misleading. That just tells you what, in terms of its angular distribution, what it looks like. But in terms of radial distribution, it's completely delocalized. It could be anywhere. But the further away it is from the proton, the less likely you will find it. It's an exponentially decreasing dependence on the radius. So again, but I'll draw some pictures in a second. But anyway, this is a sphere, right? We can say it kind of looks like a sphere. It's a sphere. All right, but it's a sphere that has an infinite radius that is something diminishing. If you think about probability as like an opacity, right? How opaque something is. This radial shell is getting exponentially less opaque as it gets bigger, as you go further and further away. So if you were to think of the electron finding it as a bright spot, you have this really bright core, but it has this shell that infinitely extends and gets dimmer and dimmer exponentially as you move away. Okay, so let's go to the next one. There are no other orbitals for n equals 1. There's only the 1s, so let's go look at the 2s. We have a normalization constant, 1 over 4 square root of pi, z over a naught. Once I write all these down, we'll talk about a naught. And then because we're at n equals 2, that polynomial part starts to kick in, that Laguerre polynomial. It's no longer a constant value. When n is equal to 2, basically the power of that polynomial is n minus 1. So there's going to be a polynomial that appears that's linear. Right? N is 2. The power of the Laguerre polynomial is n minus 1, which is 1. So it's going to be a linear function, and it's 2 minus rho That's our Laguerre polynomial. And then we have e to the minus rho over 2. Okay. If I were to hide this 2 minus rho part, we just got rid of it, right? This function doesn't really look any different than this one, right? There's no angular dependence, right? There's no theta or phi here. There's an exponentially decreasing part. It decays a little more slowly, to be fair. It's rho over 2 instead of rho. But in general, it looks the same, except for this part right here, right? There's a row where this goes to 0. That's not infinite, right? The only place where this is infinite, 1s, is at infinity. But there's a specific value of the distance where this goes to 0 that's finite, and that's rho equals 2. Right, so if I were to plot this function, let's just plot the radial function. R versus psi. Well, at rho equals 0, this is a positive number and this is 1. So it starts here on the on the y-axis, on the psi axis, and then it crosses 0 at rho equals 2. So let me call this rho instead. Rho equals 2, right? And that's the only place it crosses 0. It never returns again, right? There's only one 0 to this function, which is rho equals 2. So the function stays negative, and then it just decays back down to 0. Right? So this function drops like this, and then decays like this, something like that. Okay, so there's a point at finite distance called a node, right, where there is no probability, where psi squared is 0. Right, so what we have here is a spherical shell. It's still spherical because there's no angular dependence, still a sphere, but now it's a sphere that has concentric probabilities shells, if you will. There's some probability that it's in this region right here, and then there's this cusp, this point, this sphere, if you will, this ball, where there's no probability at all, and then the probability kicks back in again. So if I were to look at this in terms of theta and phi, sorry, that's a long way. So if you look at this function in terms of theta and phi, it's just a circle. All right, circle's taller. Right, but there's another sphere on the inside of different sign, right? So there is some probability to be inside this first sphere, right? And then there's no probability at the intersection of the two spheres, and then there's some probability here. Right, so it kind of looks like I have two spheres embedded into each other of probability, and there's this ring, or it's a sphere because it's three-dimensional, where there is no probability. Okay, so we're getting that, right? We're getting that oscillatory behavior in the radial part. We're getting an oscillatory behavior you see in a harmonic oscillator or any, right? We're starting to get a half period, a whole period, right? And there's going to be a node in between where the system goes from positive to negative. The wave function goes from positive to negative, and therefore there's a 0 probability, right? So it's starting to look like like almost like a radial wave, right? So like a wave-like radial function. Right? And if you think about what 3s looks like, I won't plot. Do I have 3s here? I don't. We could plot 3s, right? It would still look like a sphere, right? But there would be two nodes now, right? You would have a set of probability spheres or probability shells, and there are two spheres at different distances where there's 0 probability. And then 4s, there would be 3 nodes, and 5s, there would be 4 nodes, and so on and so forth. I'll draw 3s, right? So this is 2s. And so you could probably say that 3s looks like this. And then phi, there would be a Let me do a different color. There'd be an inner sphere of probability. There'd be another one, and then there'd be a final one like this. And then the sign would change. It would be, say, positive in the middle and the inside, and then negative on the outside in the middle, and then positive again on the outer shell. Something like that, right? This would be the 3 estimates, and so on and so forth, right? They have this concentric-like wave-like behavior, right? And all a sine wave is in 3 dimensions is just a sphere propagating. That's all a sine wave is. It's a sphere propagating outwards. So we're seeing the same oscillatory wave-like behavior that we see in every other problem we've looked at. It's just now we're in 3 dimensions. We have spherical waves instead of plane waves. Okay. And of course, this is the 2S one, if it wasn't obvious already. All right, so let's just look at one more. Let's look at the 210. Right, this is the PZ orbital. The 2PZ orbital. And the function for this looks like 1 over 4 square root 2 pi Z over A naught, 3/2. And then it's a 2 minus rho. We just have rho e to the minus rho over 2. And then because this is a p orbital, it has some angular dependence. There's a cosine theta term applied to it. Okay. So we know what this function looks like in terms of theta and phi. This function is maximum where theta is 0 or pi. So we know it kind of looks something like this. That one of them has a positive sign and the other one has a negative sign. Negative and positive phase. That's that one. And then in terms of R, well, notice that this doesn't have, the only 0 this function has is that R equals 0 and then R equals infinity. And it doesn't change signs in terms of R, it's always positive. So the radial wave function, let me think about this for a second. Yeah, it's like this. In this kind of exponential tail, right? The exponential tail is what gives, right? So it doesn't look like a smoothly decreasing sine wave, which is what gives these p orbitals that like teardrop lobe-like structure that they have. They don't look like two balls connected to each other. They have this teardrop structure to them. And that teardrop structure comes from the radial part of the wave function that gives it that teardrop structure. That gives it this sharp turn in at R equals 0 as you approach the node in the middle, and the smooth roll off at the edge that's exponential. And that gives you that nice teardrop shape at the edge. That's the 2PZ orbital. And again, I can draw all the other ones, the PX and the PY and the PZ. But again, all I'm doing is I'm just taking the PZ orbital and rotating it along a different axis, right? The PX orbital is I take this one and put it this way. And then the PY orbitals, I take it and I put it this way. So we've seen those already. They're no different. Okay, but the most important thing to take home from this is, again, these lobe structures are just pictures. You can't actually visualize what this wave function looks like in 3 dimensions because it's a function of 3 dimensions, and therefore the wave function is a 4th dimension. You need a 4-dimensional plot to look at these wave functions. So the best we can do is to do these cross sections at constant radius where you get these pictures of the orbitals. Another way to show it, I think this is a better way to look at the orbitals. Right, the pictures that you guys are used to of spheres and teardrops and stuff, right? Those are fixing R and having full dimensionality on the angular structure. But if you do an angular cross section, you can look at how they change as a function of R instead. And I think you get a much better picture of them. Let me go ahead and copy this image over for you guys. So these are function. These are the squares of the wave function. So these are the probability distributions. So this is like at the top, the 2s orbital. It doesn't show the 1s orbital here. So this is 2s, 3s, 2pz, 3pz, 3px, and so on and so forth. Right. And I like these a little better, right? They give you a sense of the kind of diffuseness of the orbitals, right? That they're not really well-defined shells, but they're exponentially decaying shells of probability. And so you look at the 2s, right? There's this region in the center that has very, very high probability, and then it goes to 0. There's this ring in the middle of the cross section where you never find the proton or the electron, and then suddenly it pops up again, and then it slowly decays to 0 as you go away, right? You have this kind of diffuse cloud of probability. And you can see they look like the orbitals you expect, right? This is the p orbital, right? It's got that lobe-like structure that you like. But as you can see, it's not really a well-defined lobe. It's a lobe that is diffuse and has an exponential decay as you move away from the center. It goes away this way, it goes e to the minus r. You can see that here and here. And again, as you go up and n, right, you go from 2 to 3 to 4. These are the d orbitals. These are the d's right here. These are the f's, 3 of the f's. They're not all labeled here, but you can see that as you increase n, right, the shape of the wave function is becoming more and more oscillatory. Right, it's starting to oscillate more and more as you move away from radius. Right, this is a really good example right here, or the 4s, right? And this changes signs once, twice, and 3 times. So it's starting to oscillate like this in the radial direction. Right, they look like waves. They're spherical waves. Right, and that's just the harmonic. That's right. So these are spherical waves, and most importantly, they're orthogonal. They don't interact with each other at all. They're all completely spatially separate. Electron in one will not end up in the other. Okay? And they're just normal waves, but they're in 3 dimensions instead of a spherical system. Okay, well, let's just keep this picture in mind. We're not going to tackle on problem set 4. There's not a lot of wave function discussion. We're going to talk more about energy levels, which is going to be our discussion for Tuesday. But it might be worth to keep these in mind when we start thinking about more complex systems, when we start thinking about helium, or when we start thinking about molecules and we want to combine atoms together. When we start combining atoms together, it'll be really, really important for us to consider the geometry of the orbitals in which the electrons are existing. Right? When we have 2 atoms that we bring together where their valence electrons are in 2p, those molecules look very different than molecules whose valence electrons are in 2s. In the same sense that O2's oxygen structure looks very, very different than the sodium dimer in A2. Sodium dimer has a very simple sigma bond, single bond between the 2 sodium atoms. Totally boring, totally uninteresting. And of course, oxygen has all these double bonds, lone pairs, and all of these crazy things. Right? And that's enforced by the fact that the oxygen valence electrons are in the p orbitals. Right? And the fact that they're in the p orbitals lead to different bonding motifs than the ones that are in s, simply because the electron density is different. It's in a different location. It's polarized along an axis in the p orbitals instead of it being spherically symmetric. So when you bring in 2 lobes that are polarized, they're only going to align with each other a certain way. Right? If you have two atoms of electrons in 2pz, imagine I have one atom, the electrons are coming in like this, and I want to bond it with another one. The other one's not going to bond like this. Right? They're perpendicular to each other. They're not going to bond this way. Orbitals are orthogonal to each other. But if I come in this way, they're going to bond because they're overlapping each other like this. Or if I bring in an s orbital and a p orbital, well, this might work as well, but it might not work as well, right? Because you're adding a sphere to a p orbital, that might not work. In fact, we'll find that when you take a 1s orbital and you add it to a pz orbital, it doesn't work at all. It cancels out. It's not quite clear why that is, but I'll show you. You can't bond a pz orbital to an s orbital for symmetry reasons. But a px orbital, an orbital that's lying along the plane of the bond, right? You've got a lobe sticking out this way, and then an s orbital comes in from another atom, like a hydrogen. There's no problem with that, because that positive lobe right here, right? Imagine this s orbital is coming in this direction towards this to interact. Those will connect just fine. We'll get overlap between these orbitals and form a bond. But if I take this sphere right here, we'll see, and I move it in this way along the side of the orbital, I get no net bonding. Right? So the geometry of these orbitals are extremely important for determining chemical bonding. And so I just want to keep these structures in mind, and we'll come back to them when we need them. For the time being, we don't really. Okay. So the next thing I want to talk about are energies. We haven't actually calculated the energies of these orbitals, right? So I'll just leave that for Tuesday, and let's just finish it. All right. Have a good weekend, guys.
Maybe. A sub 0.
Oh, yeah. A0. Dr. Seifert.
Oh. Yeah, sorry. One more thing, guys. For those who are interested, I'll mention it next class, but I haven't mentioned what A0 is. Let me just write it down for you guys. All right, we'll actually define it more carefully next class. Let me just go right ahead and write it. So A0 is just a constant. It's what's called the Bohr radius. Right. And we'll see how it's defined next class. So A0 has an exact value of 5.29177 times 10 to the minus 11 meters, which is 0.529 angstroms. And it's defined exactly to be a bunch of constants we've already seen before. It's defined as 4 pi epsilon naught h bar squared over the charge of the electron squared me. And what we're going to find is that the most probable distance for electron in hydrogen 1s orbital is A naught. So A naught we call the chemical length scale. On average, the electron in an orbital, a 1s orbital, is half an angstrom away from the proton. So when you take two hydrogen atoms and you bond them, you've got two electrons at 0.5 and they're going to interact with each other. So you've got 2.5 distances between the nuclei, so the total bond length is going to be roughly 1 angstrom. And that's exactly what hydrogen's bond length is. It's about 1 angstrom. So A naught defines the length scale of the electron-proton interaction, and in some sense, it is the length scale of chemistry. Okay, so we'll look at this more carefully. We'll actually derive this value, and I'll show you that, in fact, this is the correct value for this. And this is why bombs are typically 1 angstrom. Okay, sorry about that. Thank you. Thank you for the reminder. Sorry I had to jam that at the end. You too. Thank you. Yes.